Okay, so why? First of all, Despicable Me 1 was the best of the three.
What?
No.
No.
Oh, definitely. And it was because of the criminal mastermind. Okay, this character named Vector. Why was he named Vector? What did he say? Do you not remember what he said? Oh my goodness.
According
I
to
see
the directions
this
of
movie.
the actually determine the position of 1 point in space. No, you gotta look up.
That is not what Vector said in the movie.
Well, he said something like
Ah, he said he committed crimes with both magnitude and direction. Oh yeah.
Oh yeah.
Yeah, you knew that was coming, right? Okay. All right. Great character, but I have to use that every year because he talked about the two main properties of a vector. Right there is what he was mentioning when he talked about that. Yes. You might. Yes.
Oh,
glad
boy.
to see you.
Oh boy.
When are we? When are we testing for you?
No, probably never.
When would you like to do that? Oops, I better pause this. Let's. Yeah. Who's the one with the master's degree? Okay, folks. When you talk about the definition, so you understand, a vector can be drawn on a graph with an arrow. Yes, folks, that's as complicated as the graphing gets. Now, every vector has a starting point and a stopping point. When you're at parties, you should refer to them as the initial point and the terminal point. Sounds cooler that way. Initial point and terminal point. Okay, so in this picture you can see that the origin is the initial point and the terminal point is AB. You with me on that? Initial point 0, 0, terminal point AB. Stay with me. Now, you with me? So, when we graph this particular vector, it has what we call components. Getting a staple. The point, we use parentheses. Is everything okay?
Yes, get it all.
All right.
Yeah, Clarence. What's your vector?
Thank you for the airplane reference.
Roger.
Very old. Okay, now, I want you to notice that the components of this are listed with almost what looks like, less than and greater than signs. So even though the point, the terminal point, is listed with parentheses, the component form of a vector is listed with these vectorish looking brackets. Yeah, sideways V. There you go. Nice. Okay, the starting point down here is the origin. Okay, the terminal point is at the end of the arrow. Now, folks, if you're trying to draw a vector, okay, let's suppose we were drawing the vector 2, 3, okay? So we're trying to draw the vector 2, 3. This is wrong. This is wrong. Now tell me why that is wrong. Because what? It goes past the, now use the cool term, the terminal point, right? You could hear Arnold Schwarzenegger saying that, can't you? The terminal point. I can't do it very well. I'm just, just thinking here. Okay, but this would be wrong, and I see a lot of kids that do this, where they draw that vector and it goes right past the terminal point, and I'm like, wait a second, isn't it supposed to stop at the terminal point? They think they're stopping at the terminal point, but they're not. They're going past. Yes, Miss Johnson.
So, when do they use the these in the parentheses?
Yeah. Oh, well, most of the time, most of this chapter, folks, you're going to be dealing with these brackets. Most of the time. In the beginning, we're showing you, okay, here's the initial point, here's the terminal point, and so we use the common parentheses for those points. But most of this section, you're only going to be looking at these, at the vector sideways v's.
So they're just like substitutes.
Yeah, basically. Now, how do you get from this point to this point? Don't you use the legs of the right triangle? I mean, that's what the coordinate system is based on. We call it the rectangular coordinate system because you're following rectangles and the legs of the triangles. So, what is the length of this side of the base of that? That is A. And what is the length of this side? B. That's how you get to the end of that vector, right? You go A units to the right and B units up. Just like for 2, 3, you go 2 to the right and 3 up. So, I'm hoping that you're getting the idea that we're going to be using a lot of right triangle trig. And what kind of things come to mind when we talk about right triangle trig? Sadness? No, not sadness. SOHCAHTOA. It's the easy stuff, right? Okay? None of this, prove this secant theta times the cosine of pi over 2 minus theta. Okay, we're not doing that. Okay, we're just doing right triangle trig for a lot of this. So I'm hoping that comforts you a little bit, that it should be pretty familiar to you, right? We've done a lot of this stuff. So that's got a side length of 2, that's got a side length of 3. Hey, can you find the length of that red arrow right there, that vector 2, 3? Can you find the length of it? Yeah. Okay, do it. Find the what? Yes, let's use the Pythagorean Theorem. I'm not sure. Have I mentioned the fact that I was really concerned when I found out that the Pythagorean Theorem we named it after him, but he wasn't the guy that figured it out. That really bothered me when I found that out. Okay. The length of the hypotenuse, that's the length of that vector. So the length of the vector is called, what'd you say it was? Square root what? 13. Okay, folks, you just found what's called the magnitude of the vector. I'm running out of room here. How can I what? Okay, so remember, Vector talked about committing crimes with both magnitude and direction. The magnitude is the length of the vector, which you already know because you've already had geometry. That's not a real tough concept. I knew you guys would pick that up pretty quickly. Now, could you find... Could you find this angle for me right now? Use your calculator, find the angle. You know it's the vector 2, 3, so you know what the components are. So find me that angle. Okay, so I heard one person say that the tangent of theta equals what fraction? 3 over 2. So in my mind, this would be the way to go, right? Did a little tangent inverse, right? How did the calculator go?
6.1 degrees.
Oh, there's tangent inverse, 3 over 2. 56.3 degrees? Okay. That's a rounding issue, that's all.
So
I have 0.09.
next Friday at this moment, I will be
I don't know. So let me try your method. So it was suggested behind me that we could do another method. Could we use the law of sines here? It's a weird flex? Well, but okay.
Oh wait, actually, you can do any of them, really.
We could do the law of cosines too. Yeah, we could do all three of them. But you're right. Choshika would be, we don't have an inverse cotangent or inverse, cosecant or inverse secant button. So we'd still have to change it into cosine, sine, or tangent. But yeah, we could use any one of those. A lot of you will probably use the ones that are given to you and do tangent in order to figure that out. I don't know why I put an equal sign in there, folks. You should have stopped me. You can't say equals that. It equals theta. Theta 56.3 does not equal 3 over 2. What was I thinking? I don't know, guys. I know you guys like to do that. My son, my 7th grade son likes to do that all the time. Just equals, 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 equals. I'm like, no, that's wrong. You can't do that. I understand in his mind, he's thinking process. He's thinking the next step, the next step, the next step. But got to do things the right way. Whew. I know. So guess what? All of these terms that you see here, vectors are two-dimensional, sure. All right, they got an x and a y. They come in a component form, but you guys already kind of have that sense or understand that it's the legs of the right triangle. Magnitude is the length. We just talked about the length of the vector, and you guys know how to do that. And the direction, you guys know how to do that. You really have done a good chunk of section 1, and some of this is all stuff from geometry you already knew. Okay, now the zero vector. Ooh, that's popular, right? The zero vector. How long is the zero vector?
0.
Yeah, because it starts at 0, 0, and it stops at 0, 0. I know. I'm like, that's like a dot. I'm like, so yeah, that's, hopefully nobody calls you the zero vector. That'd be a cruel name. I don't know. People are bullies, Okay. Example 1, show that the arrow from R -4, 2 to S -1, 6 is equivalent to the arrow from P 2 -1 to Q 5, 3. Okay, now, the question behind me was, can we just do slope? I don't know. Let's use that logic and see what we can do with this. They look the same. Who in the world says that? I like this. I like thinking like this idea of slope. Now I know you probably would be estimated to be correct, but we need to verify it, okay? Because we want you to do well on the quiz and test. So what do you do with those? If you subtract those, what do you get? 6 minus 2? Well, that's 4. Okay, all right. Okay, 4.
Oh wait, that's not even right.
Okay, how about -1 minus -4?
3.
3. See that right triangle? What do you think the bottom edge is?
3.
What do you think the vertical side is? What's the component form for this vector? 3, 4. Good job. So the idea that you were mentioning about slope, smart idea, right? Because you really are just finding the sides of that triangle. That's the component form. Now, if this other vector is the same, what do you think is going to be true about this other vector? The component form has to be 3, 4. So, now, Ms. Hands, you asked me a question. You said, what are you doing a few seconds ago? Well, I like to write my coordinates one over the top of the other because then I like to circle the y values. You know why I like to circle the y values? Because I see kids that they use a y and an x together. So I like to line them up vertically That way I don't make mistakes. So what's 3 minus -1? Ooh, 4. Looking good so far. How about 5 minus 2? 3. Hey, we got a winner. Right? Because we got a component form of 3 and 4. Okay? Nice. Okay, so those vectors are the same. Now, describe to me what it means for two vectors to be equal vectors. If I said that phrase, equal vectors, okay, so magnitude would be the same. Component form would be the same. And you said direction would be the same? You would be correct. Okay, now, if I asked you about 3, 4 and negative 3, 4. Are those equal vectors?
No, they are not.
They're not?
No, wait, they are.
Okay, you said it, Mr. Beaujolais and Mr. Wilhelm. You both made good observations. One of you said that the direction was wrong, and one of you said the magnitude was the same. See, they have something in common, right? But they're definitely not equal vectors. And just because they have some pieces that are the same, I mean, we could have the magnitude of the vectors be identical. But if the direction is not the same, then you cannot call them equal vectors. You can only say that the magnitudes of the vectors are the same. To be equal vectors means they have to have the same magnitude. If they have the same components, by the way, folks, if they do have the same components, will they have the same magnitude? Yes. If they have the same components, will they have the same direction? Yeah. So it really boils down to they have to have the exact same component form. Do they need to start and stop in the same place? No. See, this vector here and this vector here can be the same equal vectors. They just start and stop in different places. Correct. The components are the x and the y of the vector. Now, I don't know if you've ever watched the weather. Sometimes they'll have weather maps of the jet stream, and they will show arrows moving, right? The longer the arrow, what do you think is happening? If the vector's longer, what do you think that means on a wind map?
The wind is more intense.
The wind's more intense. It's moving faster.
Yeah, bigger wind.
Right? Bigger wind.
That's what he said.
That's right. That's right. Okay. But you see, there are lots of times where we use vectors. You just probably don't think about it. Yes.
And the one where it's 3, 4 is not equal to -3, 4. How is the direction different? Isn't it pointing the same way?
Okay. So good question. So 3, 4 is over here. All right, that's that's 3, 4. -3, 4 is over here. So even though they share some common pieces, and they definitely share the same magnitude, they are not equal at all. Would I like to draw 3, -4? 3, -4. Okay, so that's 3, -4. And then -3, -4. I don't know. Mr. Beaujolais just asked if I wanted to. Kind of felt like it a little bit, so I said, sure.
I have a quick question.
Yes.
So, like these,
Yeah.
you know how they're the same there? That's just like the measure of the magnitude. And
The-
then like right here. Like
So the
are
components 3, 4 for both of them are the same, which means those vectors are equal. All I was asking was, if the components were 3, 4 and -3, 4, would they be the same? And the answer is definitely no. The ones in this example are definitely equal. Okay, I was just trying to show that, you know, if you change a sign on a component, it's deals off. Okay? How many of you feel like you need to write this down? How many of you think you need to write it down? I just want to know. What are they really put? The magnitude and what formula do we use? No, magnitude was not slope. Magnitude was the length of the vector. How did we find the length? It's the Pythagorean theorem. You just did that, right? So I think you all know this. I don't think you really need to write anything down. I know that they have what looks like the cool distance formula right here from geometry. It's still the Pythagorean theorem. I know it looks weird, but it is still the Pythagorean theorem. Okay. Find the magnitude and the direction. All right, let's see if you can do it. Find the magnitude and the direction. Okay, now they gave me the starting point and the stopping point. What do you think would be smart of you to draw right now? A graph. Go for it. Draw a graph. Find your starting point. I'm glad we won, but 13 is a little bit close for round one. I have no idea. All I know is we have one more game, that's all. You can just leave a square root 8. I'm not that picky. Okay. -3, +4. 1, 2, 3, 4. So -3, 4. That's my P. And then my Q, -5 and 2, right. Please make sure that you drew, does everybody draw their vector like that? It has to have the right starting point, the right stopping point, and the arrow in the correct spot. It always has to start with some starting point, and they gave it to me right there, -3, 4. Okay, look at this, because it shows me it starts at P and stops at Q right there. Okay, now, what do I need to figure out about this vector? Before I get to magnitude and direction, what do I need to figure out first? Yeah. How do we say that? You're right. Yes, Mr. Zemmel. And yes, we need to find the components. So a few of you have said we could do the subtracting. One of you said, why don't I just count? Okay, or I should have drawn that the other way. Sorry, my bad. We'll go left and then down. Well, you can, to be quite honest. So, and in fact, I probably will just to draw my picture, but just for my, my argument's sake, if you kind of were envisioning this to be the origin, it would be left first, and so we would go -2, and then what? -2, -2. So that's the component form of this. Okay? And you know what? I'll just leave it like this. That's fine. Unless I counted wrong. What is it? -3, 4? Okay. Correct. So imagine point P right there is like the origin. And if you have to get yourself down to Q, you would have to go left 2 and then down 2. So some people do this. Watch what I'm about to do, folks. Some people slide the entire vector so that the starting point is the origin. Would that be okay? Would these be equal vectors?
Yes.
Sure they would be. They have the same magnitude in the same direction because they have the same what? Be more specific with your terminology. Components.
Components.
Okay, if that's what you meant, I totally agree. So, yep. Question?
Oh, when you do the when you like subtract, do you always subtract the starting point from the ending point?
No, it's determined from the initial, right?
You would have to take the terminal minus the initial, okay, to get that. Okay, so 2 minus 4 gives me negative 2. Okay, so terminal minus initial. Here, I'll write that down so that the people at home can practice with us. Terminal minus initial. What? Yeah, I am. Trying to trick me.
Again.
It would make me mad if I did that. Okay, now, so we have our component form. Whether you think about it up there with P and Q or whether you look at it in terms of this other triangle starting at the origin, it's the same exact vector. Okay, now, how do I find the magnitude? Okay, so I got a negative 2 there and a negative 2 there. So let's find that magnitude. So the mag equals, yeah, that's short for magnitude, not magazine. Okay. The mag is, let's see, what we've got, square root of a squared plus b squared. And so what do we get? Square root of 8. Do I need to know that it's 2 radical 2? Nah. But you can do it if you want. I mean, if you're not going to sleep at night because you didn't do 2 radical 2, then you go ahead and change it. Okay, I don't want to hold you back from sleep. But radical 8's just as good for me too. I mean, truthfully, in the application problems, we're going to be actually taking the calculator and taking the square root of 8 because maybe the problem is in miles and we want to know the miles. Or we want to know the wind speed. So we would actually like to know in miles per hour. So, I mean, most of us don't have a scale that says radical 8 on it. You do? You have one of those at your house? Your cars and radians? The speedometer? Oh, wow, that's cool. Crack me up. All right, so how about the direction? Now, we need to be careful with this one, folks. I need you to find theta. Okay? I need you to find theta. That will not be the direction, but you will be much closer to answering the direction if you find it. So, please find theta. Okay, not to be confused with theater. Okay. I'm definitely not trying to, definitely don't draw your line to the y-axis. Let's avoid that. Because you'll end up reversing all your trig functions and getting confused, and I don't want that to happen. Okay, did we get theta? Tangent inverse of negative 2 over negative 2, opposite over adjacent, and hopefully several of you got 45 degrees. Okay? That is not the direction. But it will be used to find the direction. Okay, now, direction is measured on the Trig scale. Direction is measured on the Trig scale. On the Trig scale, 0 degrees is over here, and 90 degrees is at the top, and 180 is on the left, and 270 is at the bottom. Direction is measured on this scale. So, if you're down here with a 45-degree angle in quadrant 3, what is the correct direction. No, I'm not talking compass directions. I'm just talking about directions on the unit circle. It's going to be better. It's going to be bigger than 180, folks. 225. That's right. If you're at 180 and you go 45 past 180, you're at 225 degrees.
Oh, okay, I understand.
Okay, because we went, so we needed to find that 45, but then that takes us down into quadrant 3. Yes, Miss Johnson.
So why are you in quadrant 3?
Because the component form took me down there. -2, comma, -2 takes me into quadrant 3.
So you do it based on the triangle. Oh,
So if it was -2, 2 would be 135.
Correct. Good observation. You would use that reference angle. I don't know if you listened to what he just said, but he said if you do -2, comma 2, so that's putting him up here. Whoa, way too far. Seriously. I think my scale on the bottom is way different than my... But if I went up here, it would be 135. You're right. So you would use that 45 degrees and come backwards. And some of you are going to get frustrated in homework because you're going to say, well, I thought we were supposed to take the reference angle and add to 180 every time. That's only if you're actually in quadrant 3. If you're in quadrant 2, as Mr. Beaujolais just suggested, you would subtract that from 180. What if you're down in quadrant 4? You would subtract from what? Folks, if we get down here in quadrant 4, you're subtracting from 360. So your reference angle has to be taken away from 360 because you're trying to find this direction, which is coming all the way around to here. Don't mess with the y-axis when it comes to this stuff, because you'll end up getting majorly confused. I'm not saying you couldn't do it with the y-axis. I'm just saying it's not the greatest path to walk down. Yes, we will have to do more of these. Yes. How are they not equal? Okay, well, these triangles were. Okay, which is exactly, okay, now, Ms. Koob asked the exact same question. All right, she said, well, she got all confused when we got over here because, you know, she was wondering why I was saying that they weren't equal. Well, if you'll notice, I switched things up. I switched the components up. So I added a negative to the x component. That's what caused them to be not equal vectors. But these two in this picture definitely are equal vectors. Okay, I was just giving an example of when they were not. Okay, so good questions. I'm glad you guys are thinking and asking. Okay, now, resultant vectors. That's a cool word, man, resultant. Yeah. I gotta think what that word reminds me of. Not consultant. No, I gotta think of what words that comes to mind. No, it's something else. I can't think of it. I'll figure it out at lunchtime. All right, now.
resolution.
A resultant vector is when we add two vectors together, which we will need to work at here in a second. I'll show you the picture of. We probably won't get to these particular. You might get. Yeah, we'll get to these in homework. This isn't really that hard. Okay. Well, you complaining already? Mm-hmm. What does it look like I'm doing with the x components and the y components? Adding them. That's exactly what you're doing. So let me give you an example and see if you can handle this. 3, 4, 2, -1. Find the resultant vector. 5, 3. Look at you, man. That is awesome. That's as hard as finding a resultant vector is, folks. But you need to do it in component form. Okay? Did you hear that? You need to do it in component form. Now, I know at the moment that doesn't make any sense to you. But when we get down the road and we're not dealing with component form and you need to add two vectors together, we will need to come back to component form. Now, a scalar, if you're using that term at a party, is just a plain old number of the universe. It's not a vector. It is a number. So if you want to take a vector such as 2, 3, and you want to multiply it by 5, which means you are lengthening the vector. How do I know that I'm lengthening the vector? Because I'm multiplying by a number larger than what? Larger than 1, kind of like the scale change idea. If it was a number smaller than 1, I would be shrinking it. So if I multiply by 5, what does it become? 10, 15. That is also as hard as that gets. Now, this is not, yeah. Now, we will have to bring this image back up tomorrow and discuss it because we're going to run out of time here. But, yeah, tomorrow. Sorry. I didn't catch the joke, but I know that Saturday's tomorrow and I'll be here anyway. I'm just kidding. I'm just kidding. You don't have to. No, I'm not. But we do need to talk about this picture tomorrow.